Oh, they
Oh,
they say you have something you can do under host tools, and they don't. You have to go to more and do it a second time there.
yeah, it's telling me this meeting is being recorded.
I
Yeah.
know. It's just it drives me crazy that they oh anyway, let's resume the share. All right. So now everybody can see the stuff that we're doing. This is what part of it is what we saw last week. I'm going to go through it rather quickly since we saw most of it last week and get on to the new material.
This is a
Um,
very small meeting.
yeah, well, I have been losing people a lot. So, okay. So, um, we're going to go through all of this stuff today. We went through the Picard iteration last time. I'm not going to do that again. So that was the best figure picture I could get of Llewellyn Hilleth Thomas. Really very poor. Then, of course, there's Fermi, who did all of this stuff. All right. So we've been looking at various ways to solve ODEs using perturbation methods. We had a whole lot of problems with that for the Thomas-Fermi equation. So I decided to see what we could do with collocation. So we talked about Foreman Active, the head of the Princeton mathematics department, and some of the stuff that he talked about being done. He had basically said, stay away from collocation. It's only something that can be done by a genius, not with normal people. I'm going to try and show you that after about a decade after what he said, we actually did figure out a way to do it. So, first one was just for Stephen, and that was about the Picard iteration. And basically, we showed that as you kept doing more and more iterations, you'd add every second iteration, you'd get another accurate term in the Taylor series. So even though there were tremendous numbers of terms that were not relevant, when you looked at them, they all went to zero in the region where the open interval was. So that was it's very hard to remember doing things about infinite series because they're not commutative, they're not associative. There's a whole bunch of stuff that you normally think about that you just can't do. Okay. So we also talked a little bit about finite dimensional polynomial vector spaces. And so if you remember, we were looking at 1x, x squared to x to the nth, where some n was a integer. And in order to have a vector space, you need to have a inner product. So for a polynomial vector space, a inner product similar to what would be done in quantum mechanics. That is, you could use the integral from -1 to 1 of f times, and usually you do the complex conjugate of g, and we're assuming everything's real. So you want to make sure that everything is orthogonal, which means that the inner product of the various polynomials will be equal to the Kronecker delta. If I equals j, it's equal to 1. If they're not, it's equal to 0. So if you got those integrals for the basis that I suggested, you definitely do not get a diagonal matrix, and they're not all 1. So obviously not orthogonal. So how do you change it into an orthogonal basis? Well, as Stephen pointed out last week, you'd use the Gram-Schmidt process. And that takes a finite linearly independent set of vectors and generates an orthogonal set that spans the same k-dimensional subspace as you're working with. And of course, this also works for infinite dimensional spaces such as Hilbert spaces. Okay, so how does the Gram-Schmidt work? Well, you need to project a vector onto another vector. So the way you do that is the inner product between the two vectors, the inner product of the vector you're projecting onto and the vector that you are projecting onto. So then you can iteratively find each of the new ones by taking the old vectors v sub j and taking the projections of the previous ones. And then at the end, when you've got the various vectors u sub j, you divide it by the norm of those vectors, and that gives you a normalized version. So then all of the u sub j have inner products that are either are Kronecker deltas. So I took the bases 1 through x to the 5th, I guess, 1, 0, 1, 2, 3, 4, 5. Yeah. So I took the 1x, x squared, etc., did the Gram-Schmidt, and got these particular polynomials as the result. And this can be done for many different intervals for the inner product. And each one can also have a weight function inside that inner product where here. So you can have an omega of x in front of the f of x, g of x, and that changes the corresponding polynomials. So if the weight function is 1, which is what I showed previously, then the polynomials are Legendre polynomials. If you use 1 over the square root of 1 minus x squared over the same interval, minus 1 to 1, you get Chebyshev polynomials of the first kind. If you use the square root of 1 minus x, that is 1 over the previous omega, then you'll get Chebyshev polynomials of the second kind. If you use e to the minus x squared from minus infinity to infinity, then you'll get Hermite polynomials. Those are, of course, very important in quantum mechanics. For x to the alpha, e to the minus x, and you're only working over 0 to infinity, then you get the Lagarde polynomials. And if you've got 2 parameters, alpha and beta, you can get the Jacobi ones. Anyway, so there's a whole history of how everybody does various kinds of orthogonal polynomials. And it is all a function of knowing the inner product and knowing the weight function and the interval. Okay, So the ones we had, I showed on the left, and on the right are the Legendre polynomials. And if you take a look at the first three, those are exactly the same, except you got to pull out the 3 from the x squared. So you get x squared minus 1/3, and you got a 3/2 in front. But if you look at all of these, you'll find that they're all exactly the same polynomials, which you would have expected, I hope. At least I hope you should have expected that. All right. So the next thing we wanted to do was to figure out how to do integration that wasn't so numerically extensive. One of the problems that you have is you often have very small intervals and you have to do a lot of numerical computation in order to get the results. Gauss in 18 something, 59, whatever it was, he found a new type of doing that using the appropriate orthogonal polynomials for a particular weight function. And I looked at his paper and it's almost unreadable, not because it's in Latin, because I got an English translation, but because of the way he did it. It was just really hard to figure out what the heck he was doing. But in 1826, Jacobi, he did all the work that we currently know, understanding the basis of the interval over which you're integrating and the weight functions, etc. And the way it works is that for whatever your inner product is, you find the appropriate orthogonal polynomials. Then, if you find the roots of the nth degree polynomial, then those will be the nodes of this sum I equals 1 to n of f of xi. And then the weights are done, where was it? Oh, didn't I show it? Sorry. All right, there's a way of computing the weights based on the values of the nodes. And I thought I had it in here somewhere. Anyway, so you wind up being able to integrate polynomials of degree 2n minus 1 exactly using just n points and n weights. So normally everything you do would be, if you have n points, you'll be able to integrate n degree polynomials. So this is almost twice as good. Okay. So why are we doing this? Well, the Galerkin method that I was talking about a couple of weeks ago, or I guess about a month ago, is doing, you need to do a bunch of residuals, and then you're basically doing least squares on the residuals and finding the coefficients of an approximation. So if you have a set of bases phi sub I of x, then you have some kind of ordinary, nonlinear or linear ordinary differential equation. And just f of y prime, y double prime, dot, is equal to some function g of x. And g and x is on the interval a, b, and there's a bunch of boundary conditions. Now, the way Galerkin did it, usually he did it for 2-point boundary value problems in ordinary differential equations. which we've done a lot of work in the past about. Okay. So the reason that we care about the uh, the Gaussian quadrature is that the Galerkin objective, is basically taking the approximation that you have for some set of basis functions, sticking them into the partial differential equation, and that will be whatever residuals you have. You square them, and then you integrate that over the interval that they work. And then you find the values of the coefficients CI that do that's solve that that minimize that objective. So it's a least squares solution. Everybody following what's going on? Any questions?
No, Bob.
Nobody's following what I'm doing.
No, but no, these words, I remember I took enough mathematics a long, long time ago, but basically I never used much of it. I mean, there's things that I needed, I did. So like Galerkin's method definitely strikes a bell, but that's been like 55 years without doing anything. So I find it interesting and it's well explained, but please don't ask me any questions.
Okay. Well, we'll do a couple of examples, one with a linear set of equations, and then we'll go on to the Thomas-Fermi. Okay. So as I said, all of these integrals, if you're doing them, you can, they're very difficult to compute. You usually have to do it numerically. And the reason of using Gaussian quadrature is that the objective, the integral from a to b of these terms becomes a relatively simple sum. So if you have a 100th degree orthogonal polynomial for the appropriate bases that you have, you just have 100 points and 100 weights, and this becomes much easier to do than what you would do everything numerically. Okay, so I had taken time to do this before, and I had thought this was going to be about the time it would be a break, but like I say, I'm trying to get through it much quicker this time. All right. So what about the Thomas-Fermi equation? This is a non-dimensionalized version of a charge density within an atom. So it starts at the origin, x equals 0, and its value, it's a charge density, whatever the amount of charge there is. This is non-dimensionalized, so it goes to 1. And the charge density goes down, monotonically decreasing until it gets to infinity, when it goes to 0. So this is the nonlinear differential equation that Fermi and Thomas came up with for this.
So the charge density is Y,
Yeah.
and the boundary conditions are it's
Y of
one,
0 equals 1, and
one,
y
and
of infinity,
got it.
well, it depends
Yeah.
upon
Oh, I
whether
see.
they're,
It's on this slide. I'm
yeah,
sorry.
if they're neutral atoms, then it goes to 0. If it's positive atoms, there's a particular region over which all of the charge density will remain. And if they're compressed atoms, then there's a different one. But basically, I've been talking about neutral atoms. So y of 0 equals 1, and y of infinity equals 0. Okay. So now Sommerfeld, we talked about this last week, but it's part of the solution thing that's going on. That particular equation has a particular solution. You can stick it into that differential equation and find out that 144 over x cubed solves that equation. Now, it very it solves that equation, but it only solves it for the boundary condition yp of infinity goes to 0. Y of 1, yp of 1 is nowhere's near, well, of 0 rather, goes to infinity. So obviously it's not a complete solution. You can do various transformations, and as I stated last week, for some reason, Sommerfeld figured out that by using this transformation for x and y, and then doing an approximation by 1 plus alpha t to the lambda. Why he would do that, I have no idea, but he's the genius, not me. And he needed to figure out what the alphas and lambdas were. Turned out that the lambdas were the roots of the equation lambda squared plus 7 lambda minus 6 equals 0. And those you can get those exactly, and they're about 0.772 and minus 7.7772. Anyway, he eventually figured out how to do it so that you could get a boundary condition of this transform version, w of 0 equals 0, which is equivalent to the y of 0 equals 1. But when you take a look at that solution around 0, it's nowhere near the monotonic decreasing behavior that you expect for the charge density. So but for anything about over 100, you will have about 10 digits of accuracy for x being 100 to infinity. So basically what you can do is piece two pieces together. You can take a solution from x equals 0 to x equals 100, and then use Sommerfeld's solution for the rest of it. And that makes it a lot easier for what you're doing. Okay. So we did a couple of different perturbation solutions. This was using the K-Bessel functions by using, if you have the equation y double prime equals square root of y cubed over x, and you let epsilon equal 1/2, then you'll have y of x to the 3/2, which is 1 plus a half, and x will be 1 minus epsilon. When you let epsilon equal 0 to get the initial solution, you get various k functions and I functions. I Bessel functions go to infinity as t goes to infinity, so those are useless. And the square root of t, k, 2 square root of t, that's a potential one. And you could try various collections of these for various k functions, and I'll talk a little bit about them later. So here's a couple of possible basis functions So you could have k functions just as a function of square root of t, and you have to you need to find out where they all go to 1 for some particular 0. So you need to shift them. You can see what K0 gives the orange one, K1 gives the green one. So if you can figure out where all of these points where they're equal to 1 are for the various shifts, then you can do a t minus the shift for each one. And they would all start at t equals 1. They all monotonically decrease. They all go to 0 as t goes to 0. So those look like reasonable basis functions for a Galerkin method. Here we have the other type, which is 2 square root of t k1. And if you look at those, they also all monotonically go down to 0. And again, if you start them out at 1, then and k0 is a problem because it goes to the derivative of that goes to infinity at t equals 0. So that's not a good solution. But starting with k equals 1 to 5, here, these are other possibilities. Again, what you need to do is to figure out what the shifts are, and then you've got t minus a shift and t minus a shift, and then everything winds up being a reasonable set of basis functions. Okay, so here's for the K0, you can find what those are, and 0.2, 0.5, 1.5, 3.2, etc. Those all are shifts for the K-Bessel function, and they all go to 1 at 0, and they all go to infinity at that. So a linear combination of these would be a reasonable solution. For the square root of t times the K-Bessel function, the K1 just goes immediately to 0. The K2 is about 2, and then 4.8 for K3 and 8.6 for K4, etc. And so you have two different types of possible solutions. You use shifted K-Bessel functions for the basis functions in Galerkin's method. Okay. This is, all right. This is going back to, I don't know why this wasn't up at the beginning, but if you have a non-trivial polynomial and you have some type of a weight function omega of x, and you have all of these k's for various n minus 1s, if they all go to 0, then this means that the polynomial's p sub n will be orthogonal. It's an easier way to compute the orthogonality. Anyway, as I was saying, for Gaussian quadrature, we pick n nodes of any particular 0, the zeros of p sub n, and then n weights. And the way in which we do, there's the weights. So if you take the polynomial and find it as the kn is the coefficient of the highest degree, the nth degree x, t sub I is each of those zeros of the polynomial. So you form the polynomial by doing x minus each of the zeros. And then when you multiply that all together, there's some normalization, which is the coefficient of the highest order power, x to the n, and that's the kn. So you can always find that out. And then for the weights in Gaussian quadrature, so you take the k, the highest power of the next highest degree, p sub n plus 1, divided by k sub n, then you do 1 over the derivative of the nth derivative at the 0 t sub I, and then p sub n plus 1 of t sub I. So that turns out to be the way in which you can compute all of these weights in Gaussian quadrature. Okay, so what do you need to do? You need to find a particular weight function. You need to find the corresponding orthogonal polynomials. You need to know the interval from A to B. In most of what we're doing 0 to 100 because we're working with everything up to the Sommerfeld solution. And I looked at various kinds of weight functions. One of them was 1 over the square root of x. You could see that from y to the 3/2 over square root of x. That might be one that would be useful. 1 over x, if you got the version where I chose epsilon equals 0 in a perturbation solution, and 1 over 1 plus the exponential of x. That one I had not heard about before, but it turns out that that's the one that was proposed by Fermi for this particular problem. So I also figured out what the polynomials were for that. Okay, how do we do the Galerkin method? Where am I time-wise? Oh, I still have 20 minutes here before we take a break. Okay. Benedict Hyman Gross. He's another New Jerseyite. I didn't know that he was born fairly close to where I was. He was born 5 years after me. Anyway, he was several things. One of them was that he was the head of the math department at Harvard. He was also the dean of Harvard. So, and a really, really good mathematician. And I watched a group theory course that he did from Harvard, and I loved his quote, "You can never know enough linear algebra." And that seems to be very true. Everything seems to be linear algebra. Anyway, so how about Galerkin? So Boris Galerkin was born in 1871 in part of the Russian Empire. Currently, it is now a part of Belarus, but at the time he was born, it was part of Russia. And his parents were quite poor. So at the age of 12, he needed to get money coming into the family. And it turned out he was a good calligrapher, something that I didn't know about, but I also happen to love. And he started working as a calligrapher in the court. And later, he was enrolled in St. Petersburg Technological Institute in their mechanics department. And he did quite a bit of work. He started his earlier work around, I think, 1909 or something like that. But the one that we use is the one that he published in 1915. And he put this forward as an idea of an approximate method for differential equations, and in particular, boundary value problems. Now, he did most of the work on ordinary differential equations, but the work has been used in many different areas, including partial differential equations, etc. Oh yeah, his first published scientific work was published in 1908 while he was in Kresty prison. Everybody in Russia seems to spend some time in prison. Anyway, the Galerkin method is used in mechanics, thermodynamics, electromagnetism, hydrodynamics, and many, many other areas. Anyway, so we're going to try and understand how his work does. Let's take a really simple linear least squares approximation problem. How do you normally think about it? Well, you've got a bunch of data, xi, yi, and you've got an approximation y equals a plus bx. You stick in the a plus b xi and take yi minus those, sum the squares, and then take the derivatives with respect to a and b, and you're going to get you set them equal to 0, and you get the lowest least squares approximation. Well, Galerkin did it differently. So suppose we take our two constants, a and b, and we call them a vector x, big X. Then I can set up another matrix, which for the particular picture that I had here, these are the xi and yi in the stuff that we're looking at. And so if you have a times x, a is the constant, so it's always got a 1, and b has got the various x values, so the A matrix is all the 1s, and all the xi's are going down the second column. And those are supposed to be equal to the y's, which are the b vector, which I've written here. So what you're trying to do is take a dot x minus b and minimize all those residuals. So how would you do that? Well, we could do many things, but one of the things that you could do is just take random vectors for a and b. That is a random a and a random b, and see how good a dot x gives for the arrows, and hopefully for some value of a and b, you'd come out near b. Okay, so I chose 10 random pairs of A's and B's here, just some set of random numbers. And I'm going to take a look at what happens when you do A times each of those AX. So here's the first one for that. So -1, -0.3, and you get this blue arrow. Now I do the second one and I get this blue arrow. And then I do, these two are very close to each other. Then I do another one and that gets fairly close. And I'm also changing I'm rotating my view because I want to show you something as we keep going. So as I keep adding more vectors in, you begin to notice something, or at least I hope you do. You notice that all of the arrows turn into a plane. So why the heck is that? All of these random variables of A and B are vectors in this particular subspace, this plane. What the heck is going on? Well, if you think about what we had before, the A matrix, there's two special vectors there. There's the one of all A's, and there's another one of the various X's. And if you think about it, since A and B are simply scalars, every time you take a different value of A and B and do the inner product with that matrix, the vector is going to be in the plane where those two vectors are. So if the one is all ones, that's A1 here, and then the A2 is all the various X's there. So if you know these two vectors, and these are just the vectors in A, you know the subspace in which every A and B is going to have the result. Okay. So what does Galerkin say? He says, well, you're going to have another vector in here, which are the B's, and there's that. That's not in that plane unless it happens to be just really lucky. So what you need to do is find the vector in that space you drop the perpendicular from that vector down to that plane. So here's B, all of the Y's, and this is the one that would give you, this is perpendicular to this plane. And the solution to your problem is to choose A and B that is here. That is, you drop this down perpendicularly to the subspace done by that, and that gives you the solution to your approximate. So you've got a subspace in here, and you're looking for a vector in that subspace that comes as close as possible to another vector. And these are the Y's. And what you do is simply project down onto that plane orthogonally, perpendicularly to that plane. And that gives you the solution of the equation. So that's what the Galerkin method basically does. Everybody understand how that worked? Anybody got any questions?
Oh, that's a good explanation. And like I said, I know I was introduced to this a long, long time ago, but not graphically.
Well, I
And
always try to do
yeah, no, and
things.
that's what I'm saying. And I don't know if I understood it then, and I'd have to think about it long and hard to get it back wrapped around today. But that sure like makes uh it is great how you can both do it and do it, I don't want to say with ease. You have to be quite skilled at doing it, but how you can explain things uh, very effectively by adding that particular element in the explanation.
Well, that's what I'm trying to do. So, okay. So, have I got any? I guess I'm at the end of this, so I should now go to another page. So this is how the Galerkin method works for an ordinary differential equation. Suppose you have, you know, uh, we'll just do a second order, some nonlinear function theta of u double prime plus u prime plus u plus some other arbitrary function f is equal to 0, along with some boundary conditions. So you need to choose a countably infinite Hilbert space, and then you choose some finite dimensional subspace in that Hilbert space. And we assume that the solution of this differential equation is um, a member, is a vector in that Hilbert space. So you now approximate the solution by taking m bases. The bases, you choose the subspace, the bases of the subspace are in S, and that's a subspace of H. So u hat is a sum from I equals 1 to a fixed number, a finite dimensional subspace, times the constants times the bases by. Where the actual solution is assumed to be the sum from I equals 1 to infinity of some set of constants times the basis functions by, which are the bases of the Hilbert space H. Okay. So for every uh, place that you have for u hat, you now determine the residuals of theta of the u hats instead of the u, and then using those uh, residuals, you orthogonally project those residuals onto that subspace S, and that's the result. So let's take a look at a couple of different examples in a Hilbert space. Suppose I take bases which are exponential of the of I and x. Those are what we normally think of as the Fourier series for a function. And we're going to use a function 1 minus x cubed while x is in 0 to 1. And we know that for an infinite number of series, the Fourier series will approximate it exactly. What happens if you use a finite number of terms? Well, if you see here for 300 terms, you have all of these stuff going around in blue around the actual solution 1 minus x squared is the green. And for 300 terms, it goes around it. For 500 terms, the yellow or orange, whatever that is, uh, that's closer, but it's going to take a hell of a lot of terms to be able to get this accurately. Obviously, if you have an infinite number of solutions, an infinite number of bases, this will converge to the exact solution. So it works, but this is a poor choice of bases. So how about if we, let's see, where am I? I got another couple minutes. I guess maybe I'll stop here and take a break um, until uh, you've had a 5 minute break. How's that sound?
I'm going to have to abandon ship about 11:20. So I'm surely not. This is for Steve, the other Steve, I'm sure. Do whatever works best for you and Bob.
Well, I can continue going. Is everybody okay doing that?
There's another Bob. I guess we have to wait and see what he says.
Bob Bukowski?
Oh, I had a phone call which I had to.
Oh, well, we're Steve has to leave in about 20 minutes. So I was thinking I would just keep doing the material here rather than taking a break. Is that okay?
Yeah.
Okay, great. All right. So let's rotate our subspace, a different one in the Hilbert space. All right. So let's take a look at the Bessel functions. And in particular, let's just look at J0, the simplest Bessel function. Well, we're going to use a set of bases, which are the 0th order Bessel function, times some constants, a sub I, times x, where I goes from 1 to infinity. And what the heck are the a sub i's? Well, think about the equation that we're taking a look at. The boundary conditions on this are x equals 0 I'm sorry, u of 0 is 1, and u of 1 is 0. So if we know all of the zeros of J0, and there are, of course, an infinite number of them, then we can use those zeros as basis functions. So the alpha sub I will be the zeros of J0. So I've got little red dots here for where they are as we go through. Okay. Then if we know those alpha sub i's and we take a look at J0 alpha sub I x, why does that work? Well, J0 always starts at 1 at x equals 0, and at x equals 1, x of alpha sub I will always be 0. So these all match the boundary conditions that we have in our 1 minus x cubed. All right, so what do these bases look like? So I switched from a sub I. You can find the zeros of any J Bessel function. Usually it's denoted mu of, so you have J sub I of mu sub I of n, where all of the n are the infinite number of zeros of J sub I. And we're using just J sub 0 here. Okay, so the first one for n equals 1, you go from 1 to nx equals 1, it goes to 0. Then the second one, the orange one, that goes also from 1 and eventually comes back to 0. So all of these bases, I've gotten 7 here, they all match the boundary conditions of the ordinary differential equation of 1 minus x cubed. So what is that ordinary differential equation? Well, what you have is minus 2x squared over 3 times u double prime plus x u prime plus u equals 1, with boundary conditions u of 0 equals 1 and u of 1 equals 0. And as I pointed out, all of the basis vectors that we just looked at, all of these here, they satisfy at x equals 0, they're equal to 1, and at x equals 1, they're all equal to 0. So those are pretty good. They look like a reasonable set of basis functions for our subspace. So if we look at the same function using these are just a different way of doing Fourier series, then of course for an infinite number of these things, you're going to get the exact answer. So the two are on top of each other. And that should be obvious from your work with Fourier series. But what if I took a really small subspace? Let's say I took the first 5 of those, not even the 7 that I showed, just 5 of those basis functions. Well, if you do that approximation, the blue is the 1 minus x cubed, and the orange is the sum n equals 1 to 5 of those basis functions, where you've used Galerkin's method to find the C sub n in here. So, as noted by Foreman-Acton, if somebody happens to be a genius and has great insight, you can get very good results with very few numbers of terms. I didn't come up with this. Some Chinese physicist came up with this method of showing how to do collocation for 1 minus x cubed. I was blown away with how good it did with this method. Okay.
It just gets better if you use more terms. It doesn't.
Oh yeah,
go,
yeah.
it,
No,
it,
as I said,
it,
if you
it,
do an infinite number of terms, it does it exactly.
Yeah.
And as you do more and more terms, it gets better and better. If you did 7 terms, you'll almost be almost exactly the same there. If you do 10 or 15, you won't notice the difference between the infinite number and the first 15. I mean, they're just really, really great. So, like I said, in the hands of a genius, not me, some genius Chinese physicist came up with this as the solution. Just really blows me away.
But that's a result of this set of basis functions, and the particular uh, differential, and that particular curve, right?
Yeah, well, you've got the differential equation here, this one,
Right.
and it's got the boundary conditions. But you can do that using sines and cosines.
Right. That was your Fourier series.
That was my Fourier series.
Right.
But, if you do that with even 500 terms, it's not even, it's hardly close. Whereas you do 5 terms in this subspace, and you get an almost perfect example. It's
What
just,
happens if you use a differential equation 1 minus x to the fifth?
I didn't try it, but I'm sure it'll, you know,
There's, there's nothing
it'll
particular
work there.
interesting.
Might need, 10
Yeah.
terms or something. I don't know. I'd have to try it. I
Yeah,
didn't
no,
work it out.
it's, I mean, like you say, it's, it's just, it's that kind of mathematical magic. It's interesting.
Yeah. Yeah. Like Corman Acted commented about a month ago, in the hands of a Feynman, you get amazing results. In, in the hands of someone like me, you get
Oh,
crap.
no, no, no. Thank you. Thank you.
Anyway, so the tricks we have used to provide an approximation to the Thomas-Fermi equation are using Gaussian quadrature to approximate the, uh, and I don't have space here. I don't know why I have it twice. That doesn't make any sense. Anyway, um, the second one was supposed to be the sum of the W sub I times F times G. Yeah. All right. So I typed the thing twice. I should have. Sorry. So this is your inner product. You've got some omega. You've got an F and a G dx. So we approximate it by doing this to be a sum of various weights times F of x of I, the nodes, G of x sub I, and that is a finite sum. And those roots, depending upon the omega that you have in here for your inner product, then the appropriate nodes are the zeros of the equivalent orthogonal polynomials for this inner product. And so, sorry, this is supposed to be a sum of W sub I times F of X sub I, G of X sub I. So I screwed that up. Anyway, so that's the reason for using Gaussian quadrature. It makes the inner products much easier. You have to choose some appropriate set of basis vectors such that the boundary conditions of the ordinary differential equations are satisfied by the basis vectors. And like I said, that's the real trick, is choosing the appropriate boundary conditions. Then you use the Galerkin method to project that onto all of the residuals onto the basis vectors in the subspace, and then that gives you your first approximation as an initial guess in quasi-linearization method to determine the final result. Okay, I was gonna have some more results, but I I didn't get enough time this week to finish it. So this is basically as far as I got. Um, and we're going to let me. Okay, any questions, first of all?
No, I- quite interesting. And I actually caught a few things and remembered a couple things, but well done, Bob.
Great.
I'm still amazed both how you can put together this even in just the week or two that you have. Uh, and I, I'm sure I see I'm still trying to sort out um, how you use these tools. Not you, I mean how they are effectively used and how somebody could sit around and have to deal with this day in and day out, like in the real world, like they're really trying to solve a problem. And I just try to imagine what their brains must be like or what their life must be like. It would be an obsession trying to solve problems like that.
Well, I spent most of my life doing that kind of thing because for all of the years that I did consulting, whether it was in banking or financial or pharmaceutical research, the whole point was to build mathematical models for what you were doing. In banking, it was, finding the appropriate uh, best combination of various assets that you could have on the
Yeah,
books.
yeah.
And in the case of uh, consulting financial problems, you had to take a look at, the next 40 years uh, of the economics of the business that they were in and try to figure out what would be a strategy that would allow you to optimize or maximize the amount of uh, not revenue. Usually, you have to do profit over that amount of time. And in pharmaceuticals, the question is, how do you do the next set of when can you decide to kill a drug uh, in the pipeline?
Yeah.
Because you start out in when they have a test tube, they have about 40,000 compounds at the start. That's 40,000 compounds. Then they start taking a look at various things, usually uh, doing various kinds of uh, tests for just, do you get any DNA breaking with this compound? Do you get any of these things? And you kill them. And then when you get past all of those tests, then you start doing animal tests. And after you do animal tests, you do human tests. And the the thing, because of the fact that the average drug that uh, goes to market costs about uh, it's it's on the order of $12 billion per compound that actually makes it through the FDA and on the market out of those 40,000. So the way in which you make money is by killing projects. And I the thing I was always trying to do was to guess, which of the, 1,000 possibilities that you have left, are any of them worth doing? Um, and if so, which ones?
But once you started developing those techniques, and when you were doing that, obviously the computing power, the methodologies were evolving along with that. Today, are not those things, those same processes and that mega data processing being done uh, uh, fairly regularly by many? I mean, the methodologies have been proven, or are there people continuing to try to improve the methodologies, not just applying what has become the the accepted legally appropriate kinds of things?
Yeah, people are trying to do all kinds of things. Um, the the biggest change that has happened has been the protein folding.
Yeah.
Um,
Well, yeah, I mean, I started working in optimization methodology for aircraft design, and we did work for NASA, and that's when we started using neural networks back in uh, the early 90s, the late 80s, early 90s. But obviously, we didn't at that time. I'd done a lot of work with using optimization techniques with finite element methodology, which was evolving and began being used in the late 60s and early 70s, and when I was in the Air Force. So, but as those methods continued to develop, everybody uses optimal finite element method. I mean, today, and so I'm just curious where we are now, and you know, who is understanding the fundamental work like you take these. It's what makes it really interesting. You go back to where this originally was being developed and who came up with the first ideas, and but I'm wondering today as an okay as an ex-teacher, who's learning the fundamentals and not just applying techniques that somebody did and absolutely not having any idea whether the results are correct and the methods are being used correctly. And anyway, that's just this old guy speaking, and
Yeah, I don't know for sure, but for the people that I've talked to at Stanford and at Berkeley, they're all of all people in those two universities are still doing fundamental methods for students.
they
It's not.
are.
Yeah, they are.
Yeah, I
They absolutely are.
I'm just curious because my grandkids are all going into college. Well, yeah, they're all in high school now, so they're starting to look at colleges and all. I'm trying to think about what because and I worked in a college which has a fairly good reputation. What where what fundamentals are continuously being addressed so that there can be new ideas or you know anyway, I'm sorry, I'm interrupting you, and I said I had to leave, and my wife's going to be asking
Well,
me where am I.
that's all I know is the people that I talk to, and I only really know people here at Berkeley or at Stanford, so I
Well,
can't talk about more than
you're
that.
talking about the 1/10 of 1%.
Yeah.
Thank you for your time and effort.
Okay. Well, let me stop the recording. Okay, stop.